Hi, we're going to start today reviewing a little bit of the classwork. This is we're going to look at page 17 and 18 in your classwork packet. The first thing that I need you to take a look at is that I made a mistake. This is Mrs. Rachel speaking. I made a mistake when I put all this together in terms of the diagrams. These two diagrams are backwards. So this is the diagram for the extreme value theorem, and this is the diagram over here for that mean value theorem. And sometimes these three theorems make your head explode because it's confusing as to which is which and what each one tells you. Intermediate value theorem, you can read this. I'm not going to read it to you, but basically this part in the braces here, or big parentheses, is really important. A function has the intermediate value theorem property, or value property, if it never takes on two values without taking on all of the values in between. So if we have a continuous function, and you have a y value here and a y value here, that your function must hit all of the y values in between, as long as it's a continuous function. And that for any y value that you choose in between these two given y values, you must be able to find the particular x value that produced that y value. That's what this says. Intermediate value theorem. I kind of think about it as intermediate, in between. We're finding the value in between these two y values. I have this enlarged pretty big. Maybe I'll shrink it down a bit. Okay. The mean value theorem talks about slopes. It basically connects the average rate of change over 2 points with the instantaneous instantaneous slope or instantaneous rate of change at this particular point. So this idea right up here, this is average rate of change, and this is instantaneous rate of change. So it relates average rate of change and instantaneous rate of change. Slope of a tangent line versus slope of a secant line. Now, I think of mean value theorem. Mean makes me think of average. Average rate of change makes me think of slope. So that's how I kind of think about the two differences between them. Extreme value theorem makes me think about extremes, maximums and minimums. And what this one talks about is that if you have a continuous function on a closed interval, that there must be an absolute maximum and an absolute minimum, and those maxes and mins can occur at an endpoint or at a critical number. And that's down here. So on this particular closed interval, the maximum and the minimums, their absolute max, absolute min, are at the critical numbers. Here's one where the maximum is at a critical number, but the absolute minimum is at an endpoint. So, and here's the other two possibilities. You can investigate those a little bit further on your own. But extreme value theorem talks about maxes and mins on a closed interval, and that those maxes and mins must occur at a critical number or at an endpoint. Okay, now let's flip over to the other side. And we have this graph here. And given the graph of f of x on the interval from 1 to 10. So we're only looking right here from x equals 1 up to x equals 10. So sometimes it helps to kind of just iron this out. But that's the only parts that we can look at, is that section right in there. Okay, identify the approximate c value that satisfies the intermediate value theorem for the k or the y value of 8 on this interval from 1 to 10. So again, intermediate value theorem talks about the y values here. So it's saying a y value of 8. I have a y value of 8. There's k right there. Y value of 8 this particular x value produced that y value. Now, there is another one right here. There is another x value that produced a y value of 8, but that's not valid because that's outside of our window. So our C value here looks like it's 1, 2, 3 and a half. So C is approximately 3.5. And there's your C value for number 1. Okay, now number 2 says to identify the approximate C value that satisfies the mean value theorem. Mean value theorem talks about slopes on this interval from 1 to 10. So I'm going to take my straight edge here and get the slope of the secant. Where x is 1 on the curve, and where x is 10 on the curve, there's my secant line. Oops, sorry. Is that better? All right, now we want to, for the mean value theorem, we want to find the places on this curve within this interval between 1 and 10 where the slope of the tangent is equal to slope of the secant. So I can take my ruler and kind of just go parallel. So the edge of my ruler is parallel to my secant line, and I'm just kind of looking for where we just skate the curve. So it looks like it's right about there. There's a tangent. And it looks like it's hitting, let's see, that value looks like, maybe 2.2 or so. So that C value is that first one here. Approximately 2.2. So here's number 2, C1. All right, now why did I say C1? Because if I took my secant line and I went the other direction looking for another tangent line that's parallel, we're going to find one up here. And I'm thinking it's right about there. Maybe that looks like, 5.1 or so. So C2 is approximately 5.1. All right. Now the last part down here, I'm not going to move my page. I'm just going to read it to you, and you have it right in front of you. Identify the absolute maximum and the absolute minimum values and their locations on the interval from 1 to 10 and identify these on the graph. And this actually is a little bit tricky because those maximum and minimum points are pretty close to our C values that we found in number 2. So on this interval from 1 to 10, the absolute maximum value is going to be up here at the top of this peak. So right there is going to be an absolute max. Now if we had this, that point of tangency right there as 5.1, then maybe we want to put this absolute maximum, it's a little bit farther. How about 5.3? And we see the y value there is probably right around 14.7 or so. So we'll say then, now I'm going to move it so I can write it, that we have an absolute maximum of 14.7 at x equals, what do we say, 5.3? All right, now let's go back and look for an absolute minimum on this same interval from 1 to 10. And again, it's really close to our last C, that number 2 C1 value. I think it's a little bit prior to that. To me, it's looking like it's dead on when X is 2. And the Y value there looks like it might be at, 2.1 or so. So let's see, we have an absolute minimum of 2.1 at X equals 2. Again, these, not again, first time I guess, we're estimating these. You're not going to get these dead on, so close. I mean, if you said your C2 was 5.2 or 5.3 or something like that, we would have to accept it. If you said your C2 was 9.9, okay, that's going to be a problem. That's not close to 5.1, so just be careful. All right, now that we've reviewed these 3 theorems, let's go ahead and take a look at those AP problems. The AP problem number 2 and AP problem number 3. It's going to take us a while to get through this, so just be patient. Thank you. Okay, the functions f and g are differentiable for all real numbers, and g is strictly increasing. So g is only getting bigger, does not turn. The table above gives the values of functions and their first derivative at selected values of x. The function h is given by h of x is f of g of x minus 6. Okay, now, let's see. Explain, so first one, explain why there must be a value r for r between 1 and 3 such that h of r is equal to negative 5. Okay, well, I think maybe since they talked about this interval from 1 to 3, I'm going to go ahead and calculate those h values. So let's find h of, let's see, well, let's write it out first. H of r is f of g of r, and then minus 6. All I did was change the x up here to a 6, or excuse me, to an r. All right, now let's find h of 1. It's going to be f of g of 1 minus 6, which, reading our table, g of 1 is going to be 2, and then minus 6. F of 2, reading the table, is 9. We have 9 minus 6, which is 3. Okay. Let's find the other one. Let's find h of 3, the other endpoint, and see what we can come up with. H of 3 is f of g of 3 minus 6. This is f of, from the table, g of 3 is 4. And f of 4 is negative 1, so we end up with h of 3 is equal to negative 7. So basically, if you think about the sketch of this, h of 1, this is h of 1 is at 3, h of 3 is at negative 7. Okay, now they're saying explain why there must be a value of r such that h of r is equal to negative 5. So these guys have to, the functions are differentiable and continuous so for everything, so their compositions are continuous. So we have to be able to connect this, which means we have to pass through negative 5 somehow, some way in between 1 and 3. Which theorem is this? We're talking about specific y values. So this is the intermediate value theorem. And we can say, since h of x is continuous, oops, I should not use that since there. So h of x is continuous because f of x and g of x are both differentiable. Remember, differentiability has the condition of continuity with it, so we're fine there. Both differentiable, and h of 1 equals 3, and h of 3 equals negative 7. By the intermediate value theorem. There must be a point of C in between 1 and 3 such that h of that value equals negative 5. There we go. Okay, so that's an intermediate value theorem. You're showing that there is a y value in between those two given y values that produce a specific y value. Okay, got that one. These are tough, by the way. I think these are tough AP questions because it's very concept-oriented rather than just cranking through some problems. All right, let's look at this next one. Explain why there must be a value C for C between 1 and 3 such that h prime of C is equal to negative 5. H prime of C is equal to negative 5. All right, we're talking about slopes here. So it's talking about slopes of tangents. All right, we don't have, and we can find a derivative for h. F of g of x minus 6, so h prime. Let's see, oh gosh, this would be a chain rule, so good practice here. F prime of the inside g of x times the derivative of the inside g prime of x, and then minus the derivative of 6, so minus a 0, we don't need that. All right, there's h prime. Now, like the last time, we could go through and let's find h prime of 1. So this would be f prime of g of 1 times g prime of 1. And let's also find h prime of the other endpoint, 3. Oops. F prime of g of 3 times g prime of 3. Excuse me. Let's see, this will give us f prime of, all right, you guys have your table in front of you. I'm not going to move my paper so that you can see the table, but verify that I'm right. G of 1 is 2 times g prime of 1. F prime of 2 is 2, and g prime of 1 is 5. This is 10. H prime of 3, let's see, this is going to be f prime of g of 3 is 4 times g prime of 3, 2. F prime of 4 is 3. We got a 6. All right, what do these two things tell me? This tells me the slope of the tangent line at x is 1. This one tells me the slope of the tangent line when x is 3. That's not helping me figure out that there has to be somewhere a place that's got a slope of negative 5. Gosh, it would be nice, like the last one, if you know, that -5 was in between 3 and -7. It sure would be nice if that -5 was in between 10 and 6, because then maybe we could pull this off, but that's not. So don't be mad, but actually this doesn't help us. Don't quit. Try something else. All right, now we reviewed these theorems at the beginning today from your classwork for a reason. We're actually going to, for this one, have to use the mean value theorem. It's talking about slope of a tangent line. So what we need to do is let's find the secant line on this interval. So from 1 comma something up to 3 comma something. Okay, so 1 comma something. Uh-oh. Which function do I use? We're trying to find this for h. So I need h of 1. Oh, look at that. We figured it out just a couple of minutes ago. H of 1 was right up here at 3. So this is going from 1, 3, up until, oh, we need 3 comma h of 3. Oh, go figure. It's right up there. AP likes to do this when they write problems, that they use pieces from previous answers in future parts. So that happens a lot. All right, so if we find the slope of the secant, which, let's see, is going to be -7 minus 3 over 3 minus 1, which is -10 over 2, or -5. Oh, look at that. That is the mean value theorem. If you find the slope of the secant on a continuous and differentiable function, there must be a place on that interval where the slope of the secant the slope of the tangent equals slope of the secant. Okay, so we can say by the mean value theorem, since the slope, of the secant equals -5, there must be a point in, for C between 1 and 3, such that h prime of C equals -5. The slope equals -5. Oh, you can't see it. I'm so sorry. There we go. A lot going on here in these AP problems. A lot of concept. Okay, if you're not quite done copying, pause and then come back and join us when you're done copying. Don't just blindly copy, though. Make sure you're listening and trying to figure this out and follow along as we go. All right, let's look at this next one. Find the value of h prime of 3. Hey, didn't we do that just a couple of minutes ago? We sure did. We sure did. It's right over here on the last problem. It was one of the pieces that we didn't help us on the last one, but we found it here. So I'm just going to copy that over so that we have it all nice and organized. So we want h was, oh gosh, what was this? F of g of x minus 6. F of g of x minus 6. H prime is f prime of g times g prime x minus 0. So now h prime of 3 f prime of g of 3 times g prime of 3, and f prime of g of 3, g of 3 was 4, times g prime of 3, 2, and f prime of 4 was 3. 3 times 2 is 6. Sorry about all the page flipping there. I just rewrote it. I wanted to have it in, you know, where that answer was in the correct space. All right, now this one. If g inverse is the inverse function of g, write an equation for the tangent to the graph of g inverse at x equals 2. All right, now to write the equation of a tangent line. So this is tangent to g inverse at x equals 2. So I'm going to set this up first. Y minus something equals slope times x minus something. Well, I know the x value here is 2, so I can plug that in. All right, now we got to talk about this for a minute because I got to figure out what this y value is, and I don't have an actual equation for g to figure out what this y value is that I could plug the 2 in, and etc. But I know that 2 comma something is on g inverse, which means something comma 2 is on g of x. So go back over to the table here, and we want to know the x value on g when the y value is 2. The y value on g is 2 is right here. That happens when x is 1. So let's put that over here. That means that 2 comma 1 is on the inverse, and 1 comma 2 is on the original function, which makes sense if you go back. 1, 2 is on the graph of g. Again, I'm sorry about all the page flipping. It'd be nice if we could get this all on one page, but we need the workspace. All right, so that means that this y value here is 1. All right, now, this thing right here, we need the slope. So we need the inverse of g prime at 2. Well, we don't have any information about g inverse prime at 2. But this is that inverse rule where this and g prime at. All right, this is the x value on the original function, which is the y value on, this is the x value on the inverse, which is the y value on the original function. So I need the x value on the original function here, g prime of 1. These guys are reciprocals. We know g prime of 1, go on back, look at the table, find g prime of 1. That's 5. This one equals 5. So g inverse prime at 2 has to be the reciprocal. So 1/5. There we go. Okay? All right, one last one. This is AP problem 3, and technically this is just one part of a particular AP problem. You don't, the rest of this AP problem we haven't learned how to do yet. So we're just going to do this one part. All right, so we are going to assume that f is continuous on some closed interval a to b and differentiable on this on an open interval from a to b. Also assume that f of a and f of b have opposite signs and f prime is not equal to 0 between a and b. show that f of x equals 0 exactly once between a and b. All right, let's make just a rough sketch if we can start to kind of iron out what this is telling me. We've got some interval here, a to b. We got to be smooth and continuous in this interval. Smooth because it's differentiable, continuous because it's continuous. Also, f of a and f of b have opposite signs. So one of them's positive and one of them's negative. We'll just make that one positive and we'll make this one negative. Could they be reversed? Absolutely. Doesn't matter. All right. Now, f prime is not equal to 0. It means I can't have any horizontal tangents anywhere. No horizontal tangents, which means I can't increase and then turn to decreasing because I'd have to have a horizontal tangent there, or I could have a cos, but I'm not going to have a cos because this function has to be differentiable. So this thing, I got to be continuous. These guys got to connect. So it must cross at least once, but it has to be only once because I can't have something like that. I can't have a function change from decreasing to increasing and then back to decreasing because I just created horizontal tangents. This can't have any horizontal tangents, so this can't exist. This must be a strictly decreasing function. The way I drew it, if I had the a and the y values of a and b reversed, then it would have to be strictly increasing function. It doesn't, that function f does not change direction, so we can only cross through the x-axis once. Okay, so now let's write this out. Let's see. We can just start by, oh, this is a theorem. What do you think? Extreme value theorem, intermediate value theorem, or mean value theorem? Come on, what do you think? Very good. Intermediate value theorem. By the intermediate value theorem, there must be a value, let's say at least one value on the interval a to b such that f of x equals 0. You might want to add in here the function must cross the x-axis in when changing from positive to negative y values. Or vice versa. However, since f is differentiable and f prime of x is not equal to 0 on the interval, f of x must be strictly increasing or strictly decreasing. And f of x can only cross the x-axis once in the interval a to b. Whew. Now you might be able to say that a little bit more concise, but all the thoughts are there, all the thinking process is there. All right, thank you very much for joining me, and have a good day. Bye.